We should be able to get 3A through to 3D done before the English guys have to leave. So let's see how we go. So our second test was on applications of calculus. So firstly we learned the rules, and then in the second one what we're doing is we're going to apply all of those rules in different situations. We're going to look at the utility of calculus. So 3A, we start with tangents. So to begin with, we might just provide a summary of the unit, those 2 pages there. And when we had tangents, we had 3 processes that we can do, tangents and both normals. We've got 3B, 3C, 3D. We're talking about what does the sign diagram of the derivative and the second derivative tell us about the original function. 3E's kinematics, 3F's rates of change, and 3G's optimization. So finding optimal solutions. The table at the bottom there summarizes the relationships between F dash and F double dash and F of X. So that's all good. Oh, now this is where we had the graphing relationships booklet. So you've already received a copy of that in term 1. And you also have the booklet on conjecture questions, which a number of them were around differential calculus. Very good. So let's move on. 3A, find the equation of the tangent 2. We've got y equals x2 on top of x squared at this coordinate. Alright, so for a tangent we need 2 things. We need a point of contact and we need the slope. Alright, now we're already given the point of contact. We're told the tangent meets the curve at this point of contact. If we're not given it, then we will be either given some x value or some y value, which we can substitute in to the original equation. Now, this is the function, and so in order to find the slope, we need the derivative function. Alright, so we've got y is 2x to the minus 2. Alright, I'm bringing it to the top. Expressing it as a power of n, then I'm ready to differentiate. dy on dx will be minus 4x to the minus 3. That's the slope function, which is minus 4 on top of x to the power of 3. And we want to know what is the slope when x is minus 1. So we're going to sub that into the derivative equation. Now, minus 1 to the power of 3, minus 1 times minus 1 times minus 1 is going to be negative 1. So we have minus 4 on negative 1, which is positive 4. So the slope of our tangent is 4. Okay, and once we have those 2 pieces of information, we're ready to go. All right, and I've mentioned just briefly before, 3 processes. We can do y-intercept form. We can do the formula for the equation of a tangent, or we can do general form. Good to be competent at all 3. When I'm doing it, I tend to just do y-intercept form. So we have the equation of a line. It has a slope of 4, and it passes through this coordinate. So when x is minus 1, y is 2. We're going to sub both of those in. Let me write that down. I'll get Vivi up for the next question. Room 14. Room 4, 14. Okay, so what we might do is we might just answer all the questions here, and then we'll look at the relationships on the graph. So 3b, we talk about when a function's increasing, decreasing. 3c, when we have stationary points, and 3d, we have inflection. And all of that is consolidated in exercise 3D.1 question 4. It should go through all of those parts. So that's where I've pulled this question from. So we've got this function, x to the power of 3, take 3x squared, and we want to find these things. When's it increasing, decreasing? When's it concave up, concave down, and so forth. So, first thing we're going to do is differentiate it and draw the sign diagram. Okay? So, f dash of x, 3x squared, take away 6x. We want to draw the sign diagram. We go, what are the roots? What's going to make it equal 0? And we can factorize 3x. So the roots are 0 and 2. And again, we know this one, it's a quadratic. It has a positive a value, which means it's going to open upwards. It's happy. So it's going to have this shape as a plus minus a plus. And we can generate that sign diagram straight from the graph if we prefer. If that's our preference, we can go straight to the graph. Nonetheless, this is the sign diagram of f dash of x, and this tells us lots of important things. All right? What is f dash of x? It's the slope function. So we know when the slope is positive, and if it's positive, it means it's increasing, we're going up, and if it's negative, it means it's decreasing, we're going down. So we're ready to answer the first part. Increasing, x is less than 0, x is greater than 2. That's when we have positive slope. Decreasing between 0 and 2. All right, next, stationary points. We can answer that from here. That means local max, local min. So let's look here. We have on the slope function, positive slope, then negative slope. We're increasing, then decreasing. Local max at 0. X is 0. What's the corresponding y value? You need to put that x value into the original function, because that's the one we're making statements about. 0. And then we can see at this coordinate it's decreasing and then increasing. So we have a local minimum at x is 2. And when x is 2, we'll have y is, we're going to have 8, take away 12, minus 4. So we've done when it's increasing, decreasing, that's part A. And we've done the stationary points. Okay, so when it's concave and convex, that's what we need the derivative, the second derivative for. So we need to find the sign diagram of the second derivative. So I'm going to differentiate the first derivative. To get the second derivative, we're going to get 6x, take away 6. This is the equation of a line. We're interested in its root, so we can jump straight to the sign. Let's do it. Sorry, don't want to go too fast. So we get 6x is 6, and we'll get x is 1. Okay, so we rearrange to find the solution that makes the line equal to 0. So that means its root is at positive 1. And this is the equation of a line, and it has a positive slope. The coefficient is positive, so it's going up like this. So it comes from below the x-axis to above the x-axis. And this line, of course, you can obtain that relationship straight from your graph as well. You can graph it and you can observe below, above. Okay, so this is the second derivative. And so what does the second derivative tell us? But when it's concave up, concave down. Negative, concave down, positive, concave up. So we're ready to answer part C. And then lastly, part D, what about the points of inflection? So a point of inflection is where it changes from concave up to concave down. There are two types of points of inflection. We have stationary and non-stationary. We should have those exhibited over here. I'll sketch them quickly. So stationary looks something like this. All right, notice how it's changed concave up to concave down, but it goes horizontal at that point. That's the special case. That's a stationary point of inflection, whereas a standard point of inflection is like this, where the slope is not stationary at the point of transition. Now here, all right, to check if it's a special case, this root on the second derivative will also occur on the first derivative. 1 is not a root here, therefore we have non-stationary, we have a standard point of inflection. X is 1, and when x is 1, y will be minus 2.
With the concave up and concave down, you've written negative 1.
Oh, thank you. Yep, good pick up. All right, so just repeat that. Stationary inflection occurs if this coordinate, this root, is also on the first derivative. So that's how you know it's a special case. But finally, with all of these questions, we can use our graph to support us. So I'm going to sketch the function here. It is x to the power of 3, take away 3x squared. All right, so just from looking at this function, we should be able to answer this approximately. Said, when is it increasing? We can look and we can see if you're going to walk along it, you're increasing until you get to 0. So we've got increasing for values less than 0, and then between 0 and 2, it's decreasing. Of course that's true, that's where it's got negative slope, and then we're increasing. All right, what else? We can see the local max at 0, 0, the local min at x is 2, y is minus 4, and there's that point of inflection right there. Okay, changes from concave down to concave up. It's changing shape at that location. So all of that we can see from the original function. Excellent. All right, so there's the first two. Do the English people sort of need to move now, or you've got a couple more minutes? Couple more minutes? Yep, excellent. All right, so let's go on to the kinematics question then. We've got 3E. Leave this off. Okay, we've got a particle moves in a straight line with this displacement function. And our displacement function is 12t, take 2t to the 3, take 1. Find the velocity, acceleration function for the particle's motion. So velocity is the derivative of displacement, and acceleration is the derivative of velocity. Okay, part B, find the initial conditions and interpret their meaning. So that means when time is 0, what's the displacement? What's the velocity? And what's the acceleration? And let's put some units there, centimeters and seconds, isn't it? All right, part C. Sorry, maybe I'll just say about part B. Another thing you could do here is really answer the question in a couple of sentences. So you'd say, initially the particle is 1 centimetre left of origin. It is moving at 12 centimetres per second to the right, and this acceleration tells you that initially the velocity is not changing. All right, it's not accelerating, so the velocity is not changing in either direction. Okay, next part. C. Find the times when it changes direction. So for it to change direction, the velocity sign diagram must change direction. So here's the velocity sign velocity function, let's draw the sine diagram of that. Now again, you could just put that straight in your calculator, all right? But we're going to sketch it, all right? We're going to work it out. So we have the velocity sine diagram is 12 take 6t squared. And we want to know when does it equal 0, so we're finding the roots. Divide both sides by 6, and then we're going to square root both sides, won't we? So we'll have t is plus or minus the square root of 2. So that means positive root 2 and negative root 2, doesn't it? We've got two solutions. Now, in kinematics, we generally only consider positive values of time. So if you think, here's 0, and the only solution we would generally consider is root 2. However, for the purposes of drawing the sine diagram, I'm going to list the other one up there as well. I'm just going to sketch it like this to show you that's not generally in the realm that we consider. We've got negative root 2, and then I'd have that going that way. And so if we're going to draw the sine diagram of this function, right, again, it's a quadratic, but this time it has a negative a value, which means it's opening downwards. So that means it would be negative, positive, negative. Okay, so how does that translate for us? Well, over the region we're interested in, it's positive, and then it's negative. Okay, and again, we can get that straight from our calculator. Yeah, this would be 1.4, but what that tells us is the velocity is moving to the right. We have positive velocity until time is root 2. That's 1.4 seconds. And then we have negative velocity for the remainder of the particle's trip. So let's answer the question. Find the time and position when the particle changes direction. So let's answer that. Changes at t equals root 2. And when time is root 2, we need to know what's its position. So we will find s of root 2. All right, I'm going to bring the function up here quickly. Don't worry about the camera on it, I'll just use it to g-solve the values, unless anyone's already done it. 12x, take 2x to the power of 3, and then take 1. And we're interested when x is the square root of 2. What's the y value? 10.3. So its position is 10.3 centimetres to the right of origin. Okay, that's where it is at after 2 seconds. Part D. At what time is the particle's 1, speed increasing, and then 2, velocity increasing? Let's sketch the sine diagram of the acceleration function, because that's going to help us answer this question. The acceleration function is the equation of a line, passes through the point of origin because it doesn't have a y-intercept, and it has a negative slope, which means over this positive region of time, we have negative slope. Acceleration is always negative. Okay, so let's flip back so we can just read those dot points on speed. So 3e, the bottom one, speed of an object is the magnitude of its velocity. If v of t and a of t have the same sign, then speed is increasing. So to answer the first part, when is the speed increasing? All right, it's going to be increasing when they have the same sign. So they're both negative for values of time larger than root 2. So let's write that. Increasing, speed is increasing, for t is larger than root 2. All right, so we have to look, when do they have the same sign? Part 2 says, when is the velocity increasing? Now, velocity is a vector. It has direction. For velocity to increase, the acceleration sign diagram needs to be positive. All right, where is the acceleration sign diagram positive? Nowhere. We don't have positive acceleration, so the velocity is never increasing. Never increasing. Okay, so the first one, speed is about magnitude, so they're both negative, which means it's getting faster in the negative direction for values larger than root 2. When is velocity increasing? That means when is it getting larger in the positive direction? Well, it's not, because acceleration is always negative. Okay, last one, draw a motion diagram for the particle. So for a motion diagram, we need the initial condition, we need where it changes direction and then some third point, some sort of final point. So let's write those down. We've got s of 0, we had was -1. We've got s of root 2, which was 10.3. And then if you do s of 3, let's calculate that very quickly. When x is 3, what's my s value? It's like 19, minus 19. Okay, so if we're going to draw that on an axis, here's the point of origin, here's where it starts, that's s of 0. After root 2 seconds, it's at 10.3. And then after 3 seconds, it's at minus 19. Okay, and what's the use of the motion diagram? We can use it to help us figure out how far the particles moved in total. Alright, what's that? That's 11.3 units, and then from 10.3 through to minus 19, that distance would be 29.3 units. So to all up together, what's that? 40.6 units. Alright, we can work it out. Okay, so that's kinematics. Alright, maybe I'll pause there for a sec for the English troop to leave. Okay, so the next question we've got is on 3F, which is about rates of change. Now remember, we've got some function with height of a pine tree here. They're the ones that grow locally. They're actually from California, these pine trees, but we grow them locally because they're a good supply of pine. We've got 20, take 97.5 on top of t plus 5. That's the height function. Okay, so that's going to tell you the height of the tree in meters for any value of time. Now, what's h dash of t going to tell you? It's going to tell you how fast the tree is growing for any value of time. So our first part says, anyway, let's answer these parts. How high was the tree when it was planted initially? That means when time is 0, what is the height of the tree? So you can just go straight in and graph this function and just g-solve. When x is 0, how tall is it? When x is 5, how tall is it? You can find all those values. So what do you get when you do that? I think it's like 5 centimeters. I'm going to sketch the function out and I'll use it to answer these questions. So we've got 20 take 97.5 on top of x plus 5. I have to use x. And we're interested in it initially. So let's get rid of these. So when time is 0, we've got 0.5. So h of 0 is 0.5 meters. All right, find the height of the tree after 4 years. So that's part A, part B. So that would be finding h of 4, h of 8, h of 12, etc. Okay, all you're doing is finding the corresponding h values. Easy peasy cheesy. C, find the rate at which the tree is growing. So this means using the dh on dt equation. Now you can actually obtain these values from your calculator. There's 2 ways to do it. The first is, when you just graph the function, you have a setting on your calculator that can say, tell me the slope as I trace along it. And so as you trace along it, it'll have the coordinates and it will have the slope of that point. So you can find it that way easy, okay? The other thing you can do is, remember, we can go y1 equals some function, and then we can go y2 equals d on dx of y1. And what that'll do is, if you graph that, it graphs the derivative of your first function here. So you can graph it and say, what's the value of the function when time is 4 and 8 and so forth. I'm going to answer it manually. Okay, well, what I'm going to do, I'm going to develop a manual argument and then use technology to do it. So here's what I mean. Here's our height function. It's 20 I'm going to bring it to the top so I can differentiate. T plus 5 to the power of minus 1. For us to differentiate it, okay, it's all expressed at the top, all is the power of minus 1. Let's do it. Ready to go. H dash of t. That goes to 0. We're left with this negative 97.5. That's going to hang out the front. And this is chain rule. Okay, so we're just at the t plus 5 to the minus 1. That's just going to be chain rule. It's going to be n f of x, n take 1, and then multiplied by f dash of x. That's the derivative of the inside, which is 1. Alright, chain rule there, n f of x n take 1. And so then what does this simplify to? Well, we've got these two negatives, so it's going to be positive 97.5 at the top, on top of t plus 5 squared at the bottom. That's the derivative function, that's h dash of t. And then we can say, alright, well what is the slope when time is, what do we ask? We're asked when time is 0, when time is 5, when time is 10. So let's do 0, what's h dash of 0? We plug it in, we're going to have 97.5 on top of 0 plus 5 squared. 97.5 on top of 5, on top of 25, sorry. 3.6. 3.9. What did you say? 3.9, and then we need a unit. Okay, so the height of the tree is in meters, time is in years, so therefore our rate of change is in meters per year. Alright, so that's how fast it's growing when time is 0, and then you can answer those other components there as well. How fast is it growing when time is 5? How about when time is 10? Okay, let's do the last one. Show that dh on dt is greater than 0 for all t is greater than 0. Now this part here, right, I think the marks lie in the later part of the question. What's the significance of the result? I'll make a mathematical argument. I think you can see this just from the sign diagram. I think that's sufficient. But let's try and talk about an argument that we can use here. So firstly, this is the h dash of t function. 97.5 on top of t plus 5 squared. So this is how you break down this kind of thing. Right? What you'll say is t plus 5 is going to be positive for t is positive. Alright, that's obviously true. T plus 5 is going to be positive for t being positive. Therefore, t plus 5 squared is going to be positive for t is positive. Alright, well, I suppose you don't need the first step because we're squaring it anyway, but I just wanted to include that to show how we can break these things down to their components and show that the sum of the components leads to some conclusion. So we have t plus 5 squared, and so then what we're going to have is we've got 97.5, which is a positive number, divided by a positive number, has to be larger than 0. Alright? Why? Because when you divide one positive number by another, it's always going to be positive. What's the significance of this? The rate of change, h dash of t, is always positive. The tree is always growing. And if we look at the graph of that, we can see it, right? It's going to approach some limiting value. It's got an asymptote, but it's going to get closer and closer and closer, but it never quite reaches that point, right? Okay, last one. Let's do this, optimization. Alright, so try and remember or ask me how you do those rates of change on your calculator. Alright, optimization. We've got a 2-litre box. Let's sketch it up. X, X, Y. And it does not have a lid. It has a volume of 2 litres, and 2 litres is 2,000 centimetres cubed. Okay, first part says explain why y equals 2,000 on x squared. Well, let's think about the volume here, which is going to be x times y. Right? The volume is x squared y, and x squared y is equal to 2,000 centimetres cubed. We rearrange this. So with these optimization problems, they don't tend to pop up in exams. Nonetheless, they're still worth doing. They're good problem solving. And the marks tend to come from these show that's, right? And even if we can't answer this part, we can still answer parts of it later on. Okay, part B. Show that the surface area of the box is given by this equation. So for the surface area of the box, right, we've got the bottom. I'm going to make this argument. The area of the box is equal to the bottom plus the 4 walls. There is no roof. There is no top. We're told it's an open top box. So the bottom has an area of x squared, and the walls, each wall is x times y. So we have 4xy. But this expression is not particularly useful because it's an expression that's composed of two variables. We want to eliminate one of them or just perform this substitution. If we substitute that in there, then we've expressed it just in terms of x. So we'll do that. X squared plus 4x times 2000 on x squared, and now we'll simplify that to what they have. Okay. So that's the area function. Now what you can do is you can graph that and g-solve the optimal solution. That's going to be the minimum surface area, right? You g-solve the minimum, it's going to tell you the x value, that gives you the minimum area, and it's going to tell you the minimum area. So we can answer that, we can use our graph to support us. But let's look at how we can do a manual argument. Find the dimensions of the box which minimises the surface area. Optimal solutions occur when the first derivative equals 0. Alright, that's always the case. That's when we have a local max or a local min. So let's find that, our optimal solutions. Firstly, we need to differentiate a of x. So if a of x is x squared plus 8,000 x to the minus 1, now we're ready to differentiate it. Yep, just behind the door, thanks. Alright, so we've differentiated it, and then I've simplified it like this. This is a dash of s, and we know the optimal solutions occur when it's equal to 0, so we're going to find the x value that makes this true. Let's get rid of that denominator by multiplying both sides by x squared. And then we'll solve through for x. Cube root of 4,000, I reckon 15.9. Here's the cube root. 15.87. So 15.9, that's the value of x. That's going to give us the minimum surface area. But let's answer the question. Find the dimensions. So the dimensions of this box, right, are going to be x times y. So we've got x is 15.9. What's this y value? Well, y equals 2,000 on x squared. So let's calculate 2,000 divided by 15.9 squared. Y has to be 7.9. Okay, so that's our answer to part C. We'll put some centimetres there. Alright, so that's the dimensions of the box, but it does say find the minimum surface area. So that's going to be A of 15.9. That's when we put 15.9 into this function. So it'll be 15.9 squared plus 8,000 on 15.9. So I've got 756 centimetres squared. That's the smallest amount of surface area we can have for the box. Right? Changing the dimensions will change the surface area. So all of that calculus process can be supported with your calculator, right? You can graph this function, and if you g-solve the min, this will be your x value, this will be your y value, and so you know what the answer is before you can even go ahead and solve it. All right, so I do recommend having a look at the revision guide. All right, so it's a good opportunity for us to pull it out. You're welcome to use your time as you see fit. We've got 30 minutes still, so use your time as you see fit. All right, whether that be doing the textbook, all right, chapter 3, or the revision guide. That's what I would recommend. But yeah, we've got half an hour. Ask me some questions about what we went through and so forth.